Okay, it's time to begin Unit 16A in our Physics 211 class. And last time we were talking about simple harmonic motion, all these equations here, how to use them, the fact that we have to use radians on our calculator now, we're getting these things, and the conversion factors you have to keep in your pocket. Well, today, 16B, we do this one. Next time, 16C, next unit is this one. So this one here is partly filled in. First, all this stuff on the top still holds, including that conversion to pi radians per cycle and all these formulae. For elastic system, as you know from watching the video, if you take Newton's law and apply it, you're going to get this relation between acceleration, right? F equals ma, right? Brings the force, there it is. And if you solve for A, you get this, plug into our standard A equation, and either A right from up here, or the A in terms of X from up there, you get this. Pull out omega squared is K over M, omega squared to K over M. Invert that with the 2 pi, frequency to period, get this period, right? That's one thing. If we go to energy conservation, you have a half kx squared is plus a half mv squared is got to be equal to total energy. Total energy is this. That gives you this for the velocity. So we've got velocity, acceleration, we've got position from up there. We've got maximum energy, whether it's all kinetic or it's all potential or it's somewhere in between. And specific values for the frequency and the period of a spring. So I want to start just by, does this really work or not? And so for that, we'll actually try stretching a spring. So if I bring this up, stretch a spring. Let's do an experiment. And so I happen to have a spring right up in here. There's the bottom of it over there near the wall. This is a, let me get that in focus. This is a 60-gram, wouldn't it be backwards? It's a 60-gram mass. If we take a ruler here in millimeters, hang it up to the top there, so it's 0 where 0 is, hang this, let it stretch down. We measured from here at the top, that at the bottom is 13.5 centimeters. And so I have the following relation here, so bring this back down. And so if I have my 60-gram mass here, stretched spring, x equals 0, stretches down by 13.5 centimeters, I can get the following, right? If we look at the free body diagram of here, it's the spring going up, it's the weight going down, mg, kx, they must be equal because it's sitting there, it's still sitting there. Actually, I can see it if you can't because I just have to twist that camera up. And so static mg is equal to kx. And so this is, if I just got what I measured, 0.135 meters. That's 13.5 centimeters. M is 0.06 kilograms, 60 grams. Gonna move it 3 times, remember? That's 9.8 meters per second squared. And so you can solve this for K. K is equal to the mg over x. Well, I'm going to just call this well, x, where this is the relaxed stretch. Oh, this is the static stretch. Probably should call it something else like D, but it works here. Anyway, we can find out K for our spring. We find the following for K. And okay, so that's 4.36 newtons per meter. Now, what we'd like to do is to test something here. So let's test the frequency we get. And so omega is equal to the square root of K over M, which if we plug into this formula here, we can actually get a little bit of a different one here. It's the square root of G over X naught, which is equal to, and you can plug in this number divided by M square root of this one. You end up getting exactly the same thing, which is 8.5 radians per second. And that's not very useful because I don't see things in radians, I see them in cycles. So I want the frequency F, which is omega over 2 pi. And if you plug the numbers into that, you get 1.36 hertz. And so now let's see how well this does. Let's count the number of oscillations we get in 10 seconds, and then we will see how we're doing. So for that, we swing this thing up here so that you can count with me. There it is. I'll hold it down here, and I'll let it go when we reach a time here, and we'll count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and a half. Okay, so I got 13 and a half in 10 seconds. So measure 13.5 cycles in 10 seconds is 1.35 hertz. Well, what do you know? Wow, and if you turn wow upside down, you get mom. Wow, that's pretty good. So it actually works. What do you know? And what this tells us is that if you have a spring, just that stretch you get by hanging the weight on, and you already know what the resonant frequency is going to be. I always find that to be pretty amazing. So if you hang something from a spring and you just measure how much it goes down, okay, you know what the frequency is going to be. Works for a spring mass harmonic oscillator. Okay, now before we head off into other examples, I want to just make a note here about some other observations about the frequencies of oscillation. For elastic systems. So here we have an example. Is a spring. Omega is equal to square root of K over M. And the way to think about this is general. Omega is going to be equal to string constant of the something elastic property over inertia. Or another way to put at it is the square root of the restoring force related over mass related. Okay, and in this example, the spring K comes in the restoring force, right? Kx, coefficient, and the mass is clearly mass related. It's the inertial mass. If we had something to do with the moment of inertia, and this won't come up until a fair amount later, but it's probably worth mentioning at this point, is suppose I have a where did I take that? Oh, I'll bring it up later. We're going to see this part come up over and over again. I'll just point us back to here when we get here. Okay, but with that in mind, let's now go to a question. What happens to the frequency and the period of an oscillating elastic system if the mass increases? I'll give you a little while to think about it. You can pause the video. More inertia. Remember, that's on the bottom, so it slows down. And if it slows down, what does that mean? It means longer period or a smaller frequency, which is of course equal to 1 over the period, right? The period gets bigger, the frequency gets smaller. And so it's clear from this relation here that if one goes up, the other has to go down. And so you can cross out both of those because they can't go the same way. They're inversely related. And our thing is it slows down longer t, so t increases, f decreases. And so our answer had better be that the frequency decreases and the t increases right here. More mass, frequency goes down. And if you look back at our table here, right, the mass is on the bottom, that gets bigger, that gets smaller, f gets smaller. If the mass is on the top here, that makes our period increase. Okay, so great. Now, spring constant increases. So that's the restoring force. Increases. And so that means it's faster. And faster means shorter t, higher f. And of course the opposite, because again, t is equal to 1 over f is equal to 1 over t. You can throw these two out again because you can't have them both doing the same thing. In our case, we just said shorter t, higher f. That's this one. Okay, so that's this one. Now let's go to a, well, let's do this one by hand. How if the amplitude increases? What do you think happens here? Well, you have frequency is square root of k over m, right? Anyone see any amplitude in there? I don't see it. The amplitude only comes into anharmonic. It's not for harmonic oscillations. And so they don't change. And the that brings us to the next exercise, which is this. Oh, come on, come on. Wake up, wake up. If I get this here and convince it to focus. Anyway, let me play with this. I'll pause this thing. Okay, at least you don't have to do that at the one in the classroom. Okay, 5 kilogram mass that's hung on a spring. Spring stretches by 2.45 meters. It's pulled down an additional 30 centimeters and release. What is its speed 2 seconds after being released? Well, we already went through this, right? This is like our experiment. To get K. But when here we want speed, so we want V. So V on the result of K, of course, is that K was equal to, if you remember, mg over x naught, where the x naught is the 2.45 meters. So this is 5 kilograms, 9.8 meters per second squared over 2.45 meters. That's K. But what we want is the speed. Speed is V minus A omega sine of omega t plus phi. We've got to pull all these things out just like we had to for the last section. We pull it down additional 30 centimeters, right? So this, oops, lost it again, didn't I? Okay, there we go. We had to pull it down 30 centimeters, so this is A. And so we can put this in of A, so minus 30 centimeters. Now remember, omega was equal to, we did this before as well, the square root of k over m, which is the square root of g over x naught. And so this is the square root of 9.8 over 2.45, and that's in radians per second. The sine of, it's the same thing for omega, is the square root of 9.8 over 2.45. That'll give us radians per second times t, 2 seconds. That gives us radians. Plus, we need to know what phi is. So what is the velocity when I release it? At time equals 0. It's released. So that tells us that velocity at t equals 0 is equal to 0. And so the sine of omega t plus phi tells us the sine of phi is equal to 0. So we'll just take phi equal to 0. So that's a 0 up here. So now these are all numbers, right? Plug it in using radians mode. You'll get sick of me saying that. I hope that means that you won't mess it up. And you get the plus 0.45 meters per second. So this is a combination of what we did before, taking this, getting it into a formula from words. Again, a little bit of stuff from the spring mass system, the elastic simple harmonic motion. And of course, this little detail you have to worry about, we're getting phi, which is kind of a trick. But remember, you just write down what you're given. At t equals 0, what is it? It's usually going to be 0 maximum or something 0. Otherwise, it's too hard. But so just put that in. And then you find that you can plug in. As long as you use radians mode, you'll probably be all right. Okay. Now, let's go on to another example. 10 kilogram mass attached to a spring with a spring constant of this oscillates an answer of 12 centimeters. What is the total energy of the system? And we have our formula for total energy for a elastic simple harmonic motion. E total was equal to 1/2 Ka squared is equal to 1/2 mv max squared was equal to some combination of the two, which you can get from energy conservation, but we don't need here because we have the amplitude, we have K, and we have M. And so that gets us into a pretty good position. We just have to plug it in. By the way, you can, let me just write this down for your information. E total is of course equal to Ke plus Pe is 1/2 mv squared plus 1/2 kx squared. And so if x is equal to 0, we have maximum v. If v is equal to 0, we have maximum potential energy, and maximum x, of course, is a. So that's how you get this and this. And in between, it's equal to that. And so whatever your v happens to be at that point, whatever your x happens to be at that point, it's going to equal to one of these two. So we could ask you, what is the energy, or what is the speed at a certain x? And you'd say, okay, we take this and set equal to that, plug in that x, get the speed. That type of problem you should also be able to do. But we'll just use this one right here because that's the easiest for us to use. And we find that E total, just putting in the numbers, is 1/2 250 newtons per meter, 0.12 meters squared. That's going to make a newton times a meter, which is a joule. That's good. Plug it into your calculator. That makes it much smaller than you think it ought to be, because you end up here with 1.8 joules, which is this one. So you went to 250 down because that's 0.1, right? If it was just 0.1, it would knock it down to 2.5 over 2 is 1/4. Because it's a little bit bigger, it's a little bit bigger. Okay, so that's this one. Now I did that. So it's time to go here. And 10 kilogram mass attached to a spring with a spring constant, same thing. What is the speed of the mass? Its displacement is 6 centimeters. Well, guess what I just told you? I told you that for a reason. It's to get you ready in the back of your mind for doing this problem. I'll write it out again for you because it's important. Ke plus Pe is 1/2 mv squared plus 1/2 kx squared is equal to 1/2 Ka squared is equal to 1/2 mv max squared. This is the piece that we want right in here. Let me fix this equal sign. And so we already know that this is equal to 1.8 joules because we just did that. And generally, you'd have to work it out if this was the only problem you had. And we want V when X is equal to 0.06 meters. That's 6 centimeters. So let's get that by itself, 1/2 mv squared is equal to 1.8 joules minus 1/2 250 newtons per meter times 0.06 squared meters squared. And so V is equal to the square root of, well, we got to take this, and that's 10 kilograms. So it's, and then take the square root. So it's, what we have on the top, 1.8 joules minus 1/2 250 0.06 squared joules, converted to newtons, divided by 1/2 of 10 kilograms. That's the half m. Take the square root, chunk in what you've got. This is equal to 0.52 meters per second, which happens to be that one. Okay, simple energy conservation. And when you have springs around, unless you have that static spring that you get a K from, if it's moving at all, then the force is changing. Force is changing in a spring. You really can't do much but to go to energy methods. And that's what we typically end up doing time and time again. And so that brings us to a conclusion almost on our elastic system, but I did want to bring one more thing up here, and that is the physical pendulum, which is to say the more general case. Well, yeah, I'll do it now. Probably should do this with the next section. So yeah, let's put this off. We're going to put this off till next section, and we'll sign off for this section. So see you next time.